Hey guys, in this video I'll be showing you how to integrate with Monte Carlo. This will be really simple, but you can apply it to more complicated problem. So the problem I'll integrate is sine x. Now, with the upper bound being pi and lower bound being 0. Now I'll show you the answer integration code. The actual answer that we should be expecting to get. So if I do sine x and make the domain pi and 0 and run it, you can see that the answer is around 2, well 2 exactly. So let's import some library. We will import numpy as np. We will import mat.lib.py as plt. We can use this to visualize the integral, and we will also import random, which is the most important library we will use today, because Monte Carlo works on the concept of randomness. Now I will run that, and now we will create let's say we will create just I want to show you the function first, just so you know what it's like. I will call it equation, and it will take, let's just call it x, and it will return x. It will return sine x. Okay, so let me just show you what this does. So equation, if I return 2, it'll return np.sine x, sorry, because sine you can't just you need to use np.sine, because it's numpy has this sine feature function rather. So if I run it, sine is not defined, it gives us that. Okay, so now I will visualize the graph, but first I'll need a list of numpy. So a list of numbers as my x-axis. So linspace I will do from 0 to pi. I'll have like around 101 numbers. Okay, now x is all these numbers. Okay, I will show you now. So if I send these x's into this function, so if I do equation x, this is all the y values when you sub this x in. Okay, now I can plot this by simply using plt.plot. And what do we want to plot? We want to plot x and or the values that we get returned from this function. So you can see it's this function, and this is what we want to integrate, and integration is basically what falls under this line. It's basically the area under this line. So Monte Carlo works on the concept of randomness. So we generate random points that are equally likely to fall anywhere on this diagram. And then we simply count how many fall in this and compare it to the total points. And then we multiply it by from 0 to 3, so by 3, and this will give us our area under the curve, and hopefully that will equal 2, which we know from here, around 2. Okay, now this is the visual. Now we will do this start. So first I will create a variable. I will call it under curve, and initially it will be 0. I will create an upper limit, which will be 2 times, no, just pi, np.pi. I will have a lower limit, and this will be 0. And now I will have points, how many points I want to generate, and I'll start with 1,000. So you can have 1,000,000 or 100,000 or 100, but the more points you have, the more room, the more accurate your result should be. That's the concept of the law of large numbers. I'll start with 1,000 just because it's fast and it should get a quite good result. So now I will have for I in range points. What do we want to do? We want to generate a random value that falls on this graph. So a random point, and that point will have both an x and a y value. So I will just do x equal random dot uniform. Our x can be anywhere from 0 to pi, right? So I will do 0 and pi, or np dot pi, or rather upper limit, because that's already np dot pi. And y will be random dot uniform. Let me spell that right. 0, and you can see why the limit is around 1. Okay, so like the maximum value that can be is around there, so we'll just say 1. And now we want to do this. We will do a check to see if a point is under this curve or over it. For that, we can simply do an if statement. If y is less than or equal to, so if it's less than or equal to the value that of this curve, then we know the point is below it. Okay, so if it's, but how do we know what that point is? Well, we simply sub in this x that we've randomly generated. So we will send it to this function, and that will return the y. So if it's like that, it will just return the y, and then if that y return is bigger than this, then it means we are below the curve. So I will simply do equation, and then we simply send y x. We send x, we get y return, and this will do this for all the numbers from 1 to 1000. So we'll do it once, it will run this, and then it'll do it another time and another, all the way up to 1000. So what do we want to do when that is true, when this equation is satisfied? Well, we want to add a sort of a point to this undercurve, which is 0. So that way we can have like a tally of how many points there are under here. So I will do this by simply saying undercurve equal undercurve. So what it is previously, so it's 0. This will be 0 on the first one. On the second, it will be 1 if you've added a tally, or 0 if we haven't, and then we just add 1. Okay, I also want to scatter. I want to have a little scatter graph. That way I can see we will scatter x and y, and we will color it. Color equal, let's say red, actually blue. And then we will have an else statement, which is anything else that doesn't satisfy this equation, i.e. it's outside this curve, and I will simply scatter graph this, and we will color it red. Now this will give us the dots, but I also want to plot this curve just so we can see the shape of it. So I will also plot this on top of it. For that, I can just simply do that here. plt.plot. It's just this equation, isn't it? X and equation equation x. Okay, that should work, shouldn't it? Because yeah, plt, and I will color equal green, let's say, and line width equal, let's say 3. Now let me run this by pressing Control Shift Enter. Now this is 1,000 points, so it should take a few seconds. There we go. So this, you can see all the points that we've generated below the curve and all the points above the curve. If I were to increase it to a greater number like 10,000, you'll get a more refiner and finer mesh, and that will be more accurate, but we can work with this. So now we have added all the blue points to this. So if I call that the under curve, we've got 654 points out of 1,000. Now to get the estimate of our integral, we will say estimate integral. We will have the area ratio, which is simply under curve divided by points. So that's the total points, and that's our ratio. And now we need to multiply it, because that's the ratio, by the area we want. So we've already said we want it from 3 pi to 0. Like if you look here, we've set pi and 0. So I will multiply it by the upper limit minus lower limit. Now if I run this, I should get an estimate. I should print this, shouldn't I? Integral, we get 2.05. Now this is very close to the value we got here. Now let me see what happens if I increase the points from 0 to 1,000 to 5,000. Actually, let me do 2,000 because I don't want it to take too long. Just give it a few seconds. You can use, my computer is really slow, but normally if you have a better computer, it'll be much faster. So you can see that this is a much more refiner, and now when I update this, I get 1.97. So again, it's really close to 2. I can run this again. The thing is that it doesn't always give you the same answer. It'll be close, but it won't be the same, because it works on randomness. Every time it generates a new random number. It can be the same as before, but that's basically 2.01. So yeah, we're really close. And yeah, that's how you do Monte Carlo integration. I hope you like this video, and let me know if you have any problems. Thank you.